probably everyone's familiar that Earth's climate at the surface is defined with respect to de-seasonalized anomalies. In other words, everything you see about how the Earth's surface temperature is changing has this big seasonal cycle removed. So I realized that for talking to people about planets, I couldn't do that because the inclination and the seasonal cycles differ. So I'm going to talk about orbital geometry and solar activity. In other words, the variations that the Earth's orbit around the sun produces on the environment from surface to space, and then how solar activity itself affects that. And then I'll try and incorporate this into this Earth's response. And what I want to show you is that the whole system is really coupled. You can't just say, well, I'm going to look at the surface and that's what the climate is. So I'm sure everyone knows this. The sun and the Earth are two black bodies basically in space. They radiate to space. But the sun provides, because it's a black body temperature at 50, 70 K, provides radiation, in other words, brightness or irradiance, in the form of a black body that peaks in the visible spectrum, provides photons to the Earth that warms the Earth's surface. Some of those photons are radiated back to space, and gases in the atmosphere absorb that. So this is the classical surface energy budget experiment. The sun comes in, it's absorbed by the land, some of it's reflected, some of it's absorbed by gases. The net effect is if you combine the sun's heating plus the greenhouse gas warming, then you get something that is the temperature of the Earth's surface. Now, the sun and the Earth both have atmospheres, so the surface is just a minuscule part, really, of the Sun-Earth system. So this is the sun's outer atmosphere, the corona. If you go up from the surface of the sun, you go through the photosphere, which is where the visible radiation comes from, that I just showed you reaches the Earth's surface, the chromosphere, which is where the ultraviolet radiation comes from, and the corona, which is where in the last talk we heard this. I wasn't quite sure what that speaker was talking about. X-rays, EUV. They actually have a wavelength spectrum. The EUV is below, sorry, I'm not meaning to be patronizing, but I did get confused. The EUV radiation is below about 100 nanometers. Then it goes into the soft X-rays and then the X-rays. And the point, it's important to know those different wavelengths because they're absorbed in different parts of the Earth's atmosphere. The Earth itself has an atmosphere, and this is a beautiful image of Earth's ionosphere glowing. It's glowing because it's the atmosphere, the thermosphere in this case, which is above about 100 kilometers, absorbs photons, excites gases in the atmosphere, which then radiate to space. So this is the UV image. And the Earth too has an atmosphere. The surface, above the surface is the troposphere. There's cooling until we come to the stratosphere. The stratosphere is warmer, and I'll show you why that is. It's because solar UV creates ozone, which absorbs solar energy again. And then the thermosphere, which is warm, again, because of absorption by solar UV radiation. So just to describe that a bit better, most of the sun's radiation at wavelengths above 315 nanometers comes down to the surface and troposphere. So that's what causes the traditional climate change as you think of climate, or at least a very small part of it, which I'll show you. The ultraviolet radiation, because it gets absorbed in the atmosphere, and that's because the sun's radiation itself breaks apart oxygen to form atomic oxygen, which combines with oxygen to form ozone. So the sun itself creates the ozone layer. So we have a layer in the atmosphere, which is the ozone layer created by the sun. This gives you the altitude at which the sun's energy as a function of wavelength is deposited in the atmosphere. So you can see how important knowing the actual wavelength is to knowing where the processes happen. Now, as we move up into the atmosphere, what happens is that the extreme ultraviolet radiation and the far ultraviolet radiation dissociates O2. So the energy needed to dissociate O2 determines the wavelength of the photons that penetrate this part of the atmosphere and heat it. So these photons excite and dissociate O2, and we have a heating because of that. Now, in addition to that, the EUV photons and the X-rays have enough energy to ionize not only O2, but O and N2. And that means that they produce electrons and ions. And so embedded in the thermosphere above about 100 kilometers is this plasma called the ionosphere. And what you're seeing here literally is as the Earth rotates, this is the blob of plasma that we call the ionosphere, created by the sun's radiation. And this wouldn't exist if the sun didn't ionize these gases. So you can start to see already how everything's... Oh, sorry. Was I... Could you hear me? No? I don't have to start again, no. Anyway, so... sorry about that. This is just to then give you a concept of how complicated this system is. We heard a little bit this morning about the magnetosphere. So if you start off from the surface, it's surrounded by the atmosphere and the ionosphere. And then surrounding that are these magnetic regions called the magnetosphere. The sun produces photons, which, as I described to you, establishes the state of the atmosphere. And it's the variability in the photons that I'm going to be talking about, because that's what produces the longer-term timescale changes. But the sun also produces a solar wind of plasma and particles, and this perturbs the magnetosphere. So this is a boundary condition in which all this atmosphere is contained. So you can see it's very complicated, and you can't just sort of compartmentalize it. The biggest effect of the sun on the Earth is the fact that the Earth has rotates around an axis that's tilted to the orbital axis around the sun, and this produces the common seasons, and there's a slight eccentricity. So we need to know how the sun's radiation changes because of this. And this just sort of shows you how that happens. So this is the orbital-driven changes in received solar radiation. When I say received solar radiation, what I mean is the radiation received from the sun because of the orbital changes, not because of solar activity. If we start down at the surface, remember I told you that when you see Earth's surface temperature changes, it's a deseasonalized anomaly. This is what the temperature changes at Earth's surface look like if you don't take out the seasonal variation. There's a dominant annual cycle. This is global temperature. And when we talk about climate change, we're talking about the deviations from this. Now, as you move up and look at the stratosphere, and here I'm showing you ozone, so I'm moving up into that ozone layer in the middle atmosphere, you can see that a number of things. Firstly, there is again a strong annual cycle, but you can see there's a semi-annual cycle appearing as well. And furthermore, you can see that the deviations are somewhat bigger from this. So it's not as easy. You can't just easily decompose or deseasonalize ozone as well as you might be able to do surface temperature because of the magnitude of the different effects. Now, when I move up to the ionospheric total electron content, I'm using this just as an indicator of something that tells us what's happening in the ionosphere. I could have used total mass density, I could have used temperature, but now you can see, yes, there's a seasonal cycle. It has a pronounced semi-annual oscillation, but by no means does it capture most of what's happening in this part of the region. Now, when we get up to the thermosphere and ionosphere, this signal here is the solar activity cycle. So what's happening as you go from the surface through the middle atmosphere up to the ionosphere and thermosphere is that there are different relative magnitudes of the solar-driven cycle from orbital changes versus from solar activity. And certainly when you're up in the thermosphere, you can't separate them because the solar activity itself modulates the cycle from the orbital changes. So it's not all that simple. And furthermore, although I've shown you here the global temperature or the global signals, when you look spatially, and this is at the surface temperature of the Earth, there's a lag. There's a one month response over the oceans, which are the blue areas. You can see that they nicely show the land masses, and a couple of months or more over the oceans. In other words, the phasing of the responses of the different regions at different altitudes is not the same, and it depends on the structure of the land mass and the ocean mass, or the composition, in fact, of the system. So this just summarizes then what 1 minute? I have 30 minutes.
Oh, sorry, 30 minutes. Sorry.
Not even I can speak that quickly. So how many? 15 minutes? But you owe me one because you tried to take one away. Okay, let's keep going. Okay. So, are we right?
Yeah. Keep going.
Okay. So this is a summary at the surface of in the stratosphere and at 30 kilometres. You can see that the annual oscillation dominates at the surface, but there's a modest semi-annual oscillation. The semi-annual oscillation starts to appear more prominently in the stratosphere and is quite significant in the thermosphere, ionosphere. So this is sort of rule number one. These things are interconnected, and you can't just think of deseasonalizing things. And I say that because the work that we've done recently is that the presence of a semi-annual oscillation in the signature of the terrestrial quantities depends on the fact that the Earth has an inclination to its orbital axis. And for looking at different planets, those inclinations will be different. So you will have a different relative annual and seasonal annual variation in your time series depending on what planet you're looking. So that's why it's important to remember that when you're looking at time series of planetary atmospheres. So having said that about the basic radiation coming into the planets, now I'm going to talk about the solar activity changes. So these are superimposed on the changes driven by the orbit. And as everyone I'm sure knows, solar activity ranges from minutes to decades. The prominent indicator that we have is the sunspot number. It's shown here in blue. This was the period of the Maunder minimum, where there are a few sunspots on the disk. When in the space era where we've made observations is actually a period of very high or relatively high solar activity. We're now going into lower activity. The sunspot number, and paleoclimatologists love, and people in general love to use the sunspot number as the generic indicator of solar activity, but it is not the irradiance. What we care about when we want to understand the effect of the sun on the Earth, we have to know what the irradiance is. And so if we look at that, this is just to show that the sun rotates. Right, so here's the sunspot number. This is the total solar irradiance. What I've heard people here call the solar constant, and it made me cringe. It is not constant. It varies. It's called the total solar irradiance. Here it is in orange. And these are from measurements made by NASA. It's a beautiful record. All the variability that you see here is real, and it's a result of two features on the sun's disk or in the sun's atmosphere. Faculae, which are bright, and if you look at an image of the sun here, you can see these bright faculae. When there are faculae on the disk, they increase the net radiation from the sun. But sunspots also occur on the disk, and they're dark features, and they decrease the radiation. So the total solar irradiance is this combination of brightening by faculae and dimming by sunspots. And you can model this time series really well by the combination of these two time series. Now, this is the total solar irradiance, so it's the integral over all wavelengths. In fact, and this is why it's, I didn't mean to disparage the speaker who confused X-rays and stuff, but it's important to know exactly what you're talking about, because here's the spectrum of the sun's radiation. Right, this is down into the soft X-rays. This is the EUV region, far ultraviolet. So, see, the variability depends on wavelength, and that's because the features, the faculae and spots that cause the radiation to vary, they depend on wavelength because they reflect they come from different parts in the solar atmosphere. So an emission from the corona, in other words, the EUV part of the spectrum, is going to vary much more than the radiation that comes from the peak of the black body curve, which is the visible spectrum. So you can't just say solar radiation varies. You have to know what wavelength you're talking about, and you also have to know where it's deposited in the atmosphere. So most of the radiation, as I said, comes to the surface. The more variable ultraviolet radiation gets deposited in the stratosphere, and then the most variable EUV radiation gets deposited in the thermosphere and ionosphere. So there's this mapping of the sun's spectrum, its variability and absorption in the atmosphere that you have to understand how these regions are changing, and hence their climatology. So what happens then when you take out or remove or deseasonalize these time series that I showed you earlier? Well, first of all, you can't do it for total electron content because it's so interwoven with the time series itself, because the solar activity modulates it. But here I've deseasonalized total ozone, and here I've deseasonalized surface temperature. So this is the record of global surface temperature change that everyone tries to understand the causes of. And this is where I think it's important to talk about climate. If climate is some combination of deterministic drivers and weather, then the drivers of climate in the surface are different from those in the ozone layer and in the ionosphere. So when you talk about climatology, I think it's important to distinguish those components. So now I'm going to go through, how many more minutes now? More than one? I have more than one. Okay, so, oh, good, okay. Okay, so I'm going to go through and show you for the surface, the ozone layer, and the upper atmosphere, a decomposition of the time series in terms of what we think are causing them to vary. In other words, getting to the causes of the climatology in the past, well, we can only really talk about the past 3 or 4 decades in some cases, or longer in terms of surface climate. So this is the surface temperature anomalies. The orange curve is a model that combines these different effects. It includes a trend due to greenhouse gases that you can't, there's no way you could not have an upward trend to explain these data. Sorry, Texas. There is a solar cycle that's quite, it's difficult to pull out, but it's there. And I'm sure you've heard the sun's to blame, the sun's to blame. The sun isn't to blame. It's doing a little bit. Most of the variability that you see on timescales of less than a year are due to variations in the El Nino Southern Oscillation and due to volcanic aerosols. So, for example, I'm sure everyone remembers there's been a decade of scientific argument about the pause. There really is no pause. All that happened was that declining solar radiation, a lack of El Nino, in other words, a La Nina phase, and no volcanic aerosols meant that this was the current natural variability of the system. This warming here was because we had an ENSO. It wasn't because greenhouse gases suddenly resumed warming the planet. So this is our current, at least my current understanding, of the causes of surface temperature climatology, separate from the orbital-driven factors. Now, these are the global signals, but to make it even more complicated, each of these factors has their own spatial distribution. So you would think that, well, the sun gets brighter, everything warms. Well, it doesn't. Here's the solar pattern. You can see some regions warm more than others. And it's the same for the greenhouse gas patterns and for volcanic aerosols. And as you would expect for ENSO, it's dominated by the tropical Pacific. The reason for that is because the radiation heats the surface and the land differentially, and it drives dynamical motions that produce these patterns that are not a direct response to the radiation. So just to explain that a bit more, the sun's energy comes in primarily at low latitudes, and so this is the gradient, the gradient from low latitudes to high latitudes due to the radiation. This is the outgoing radiation, and what happens is that the system tries to move the excess energy from the equator to the poles, and it does that in a series of dynamical motions, starting with the Hadley cell, the Ferrel cell, and the polar cell. And so this is a typical condition of the troposphere during summer solstice. So the response that you see in temperature is as much an effect of these dynamical motions that not only persist from the equator to the poles, but also affect the zonal flow around the globe. Because, you know, those of you who've been following the decay of Arctic ice, the decay of Arctic ice is changing this balance, and what that does is change the polar vortex, which becomes more sluggish as this, this gradient decreases, and that changes the winds that circle the planet. So you can see that by changing the radiation from the sun, you initiate, or in fact by greenhouse gases, you initiate a whole slew of dynamic factors that you have to understand for the climatology. And this is just to demonstrate that there are many paleo observations of the effects of the sun on climate, and they all seem to make their way into Nature or something. It's all very dramatic, you know, East Africa, da-da-da. When you put it all together, this is the picture that I showed you earlier. It all makes a nice uniform puzzle, and you can see that you can't just take one region and say, this is how the Earth's responding to the sun. You have to look at the whole picture. And in particular, you can have rather large variations in some sites, but it doesn't mean globally that they're as large. So now I'll just show you what happens to global ozone. Completely different picture. For one thing, the temperature's decreasing, and that's because greenhouse gases, although they warm the surface, they cool the stratosphere. Volcanic aerosols have much bigger effects of warming at 20 kilometres than they do cooling at the surface. The solar cycle relative to the anthropogenic effects is getting larger as we go into the middle atmosphere. So you can see, even if you have a measure of what's happening of the climate at the surface, you can't take it to the middle atmosphere because it's quite different, because it's responding in different ways. And what's happening here now is that on top of the tropospheric circulation, we have the Brewer-Dobson circulation, and it moves mass from the summer hemisphere down over to the poles. And so the whole atmosphere then, if you look at your particular altitude or location, it's going to be the response of all these complicated patterns. So now, finally, in the ionosphere and thermosphere, so I'm moving up now to above 100 kilometres, 100 to 500 kilometres, and for reference, the space station orbits about maybe 400 kilometres or something. So we're in that region of space environment where low orbiting satellites orbit. Now remember, I said that you can't just deseasonalize this, but you can model the total electron content. And I'm talking about total electron content. Maybe you don't know what that is. It's the number of electrons in the ionosphere. Okay. And this is for real. Okay, fine. But it could be temperature if we had the observations, or it could be total mass density. And so here are the patterns now. Solar activity, because it's so large and dominates this region, modulates the annual oscillation and the semi-annual oscillation. It has its own signature. And in addition, there's geomagnetic activity, and that comes because this region of the atmosphere is now affected by what's coming in from the solar wind, because it's high enough up that it can get an effect from the magnetosphere around it. And each of these responses also have their same geographical patterns. So I hope you all appreciate how complex this is now. And if we look at, Dan might disagree with this. Doug Drog told me this is what happens. So the heat, again, the sun heats the summer hemisphere. It drives up the gases because it heats O2 in the thermosphere. It heats ozone in the stratosphere, causes these dynamical motions, and so the whole system is this complex dynamical pattern in addition to the radiative and the chemical responses. So in summary, solar-driven climatology, climatology of the system, not just the Earth's surface, of the extended environment. Orbital geometry and solar activity drive the amount of solar radiation received at Earth. And whereas for Earth's climate of the surface, you can deseasonalize it when you're looking basically everywhere else, I don't think that you can. In the lower atmosphere, geometry is the major factor. Solar activity is minor, and it's a minor component too to greenhouse gases. The anthropogenic influences dominate deseasonal surface climatology over many decades. solar-driven surface atmosphere temperature changes occur in concert with a whole slew of other things. They don't just occur on their own, and you can't just pull them out on their own. You have to understand the volcanic, anthropogenic, internal, and so on, things like that. By the time you get up to the top of the middle atmosphere and into the thermosphere and ionosphere, the signal is dominated by the sun. And all of these effects depend on geographical location, altitude, and they each have a different time dependence. Finished. Thank you.
Okay, wonderful. So we have enough time for questions, and I do apologize for the misfiring. So, yeah, no, so you did a great job.
Thanks, Judith. Could you explain the semi-annual oscillation again, because I didn't fully understand that? What's happening semi-annually?
Okay. How long do Okay, just as some background. The semi-annual oscillation is something that's been thrown around amongst terrestrial scientists forever. They sort of take it out by subtracting, they fit sines and cosines and take it out. So what we've actually been looking at recently, and this is with my colleague Mike Piccone, in fact we just submitted a paper on this to Earth and Space Science. I'm getting back to here. Okay, so the semi-annual oscillation occurs because, I need the other one, because of the tilt of the axis of the Earth in its rotation. So semi-annually, twice a year, you can see that the sun is heating the Earth and it's rotating diurnally here and here, and that's a different signature than when it's at the summer solstice. At the equinoxes, it's a different, response. The Earth is in a different situation than at the northern hemisphere, at the winter time. So it's this pattern that persists throughout, and I'll show you. You can see there's a semi-annual oscillation here. It's in phase as you go up to the middle atmosphere, and it's in phase even in the thermosphere. So what we think that is simply the radiation at those 2 times of the year at the equinoxes, basically heating the Earth, and the strength of it depends what the Earth's atmosphere is, whether it's heating the surface, the ozone, or the upper atmosphere. And that signal that I've shown you here persists, and it actually matches the semi-annual oscillation in the received solar radiation. So our understanding is that the semi-annual oscillation exists in all these terrestrial variables because the Earth has an inclination to its rotation axis, and that produces a semi-annual oscillation in the received radiation. Now, if you're looking at the response, I talked about the responses a lot, whether you see, for example, the annual oscillation occurs here, whereas you would expect that it dominate, the sun is closer to the Earth in here, not here. But the reason that this is an annual oscillation, we believe, is because it's actually produced by the semi-annual oscillation, and it's the heating of the northern hemisphere land masses, which do maximize at this time of the year. I didn't explain it properly, but the gist of it is it's from the it starts with the received solar radiation, and all the signals from the sun that you calculate for received radiation mimic what you see here. But then you can go further and look at the response, which is the response of the system.